Hi students, a little refresher video for you here on special triangles. I'm going to begin with the 45-45-90, which is also called an isosceles right triangle, symbolized here with two congruent sides and then a right angle sign. And this stems from the Pythagorean theorem, which is a squared plus b squared is c squared. So I've written some examples of what happens here to see if you can pick up on the pattern. When a is 6, b is 6, because they're, if you have equal angles, then the sides that oppose them are congruent as well. A is 6, b is 6, c is equal to 6 root 2. A is 7, b is 7, c is equal to 7 root 2. So I'm looking to see if it's true that if you're given that a is equal to b and the triangle is a right triangle, can you prove that c is equal to a root 2? So I'm going to start with the statement that's been given. I'll do this in black. So on my two-column proof, and this is just a rough proof, what they call a mini proof, I call this triangle KLM, and I said that it was a right triangle because it was given to me. That information was presented. And for number 2, is A is equal to B, it was given. So on step 3, I've written a squared plus b squared is c squared because of the Pythagorean theorem. But now I am going to put, instead of b, I'm going to substitute a in there. Since they're the same, so I probably should have put this step before this one, but anyway, I'll put a squared plus a squared is equal to c squared. And what I did was the substitution property. Now I'm going to combine like terms. 2a squared is equal to c squared. And I cannot remember the name of that property, but this is just a rough draft anyway, so I just put combine like terms. Now I'm going to solve this. So I'm going to solve each side by saying the square root of 2a squared is equal to the square root of c squared. And I don't know the name of that property, so I just put, hey, I square rooted each side. Now I'm going to simplify these. I'm going to pull out the a squared. It comes out as a, but the root 2 has to stay, and this is equal to c. So I simplified. But look at the deal. So a root 2 is equal to c, and that was what I was trying to prove. So that is why every time you have a 45-45-90, that when a and b are equal, c is just that times root 2. So if I had a square and I told you that diagonal was 20, isn't that just two right triangles? 45-45-90s. So if the c is 20, if I was proving this is equal to 20, I just now have to divide both sides by the square root of 2. So a is equal to 20 over square root 2, and we can't leave the bottom like that, so I'm going to multiply it by root 2 over root 2, and I get 20 root 2 over 2, which is 10 root 2. So each side must be 10 root 2, and I'm just trying to give you an example of how this transfers to another concept. Well, the same concept, but somewhat implied. All right, let's look at the next special triangle. This one being a 30-60-90, and here I have A, B, and C. Now I'm going to go ahead and tell you that the ratio of A, B, and C is this. A is equal to half of C, and B is equal to A root 3, and C is equal to 2A. So sometimes they'll say the ratio is 1 to root 3 to 2. That's the same thing, the ratio of A to B to C. And I want to show you that on these 30-60-90s, now remember this is the 30 because the short side is always opposite the short angle or the little angle. And of course the hypotenuse is always opposite the right angle. But let me show you a proof on this as well, a mini proof, a rough draft. Okay, I'm going to do this a little bit differently than the last one. Given that KLM is a 30, 60, 90, prove that B is equal to A root 3. So I could prove any of these, and I can only prove one thing at a time. So I'm going to start with that, or that's all I'm going to do. But let me show you how it works. I'm going to take A squared plus B squared is C squared, and that is the Pythagorean theorem. So, okay, I should have probably said that in my given that C is equal to 2 times A. I wish I had. So let's just suppose I had, and so I substitute 2A quantity squared for that C with the substitution property. So now I'm going to expand that, simplify that, equals 4A squared, and I'll call that simplify. Again, this is just a reasoning more than a proof. I probably shouldn't have even set it up as proof, but still. So now I'm going to isolate B and say B squared is equal to, I'm going to subtract A squared from both sides to get 3A squared. So they call it subtraction property, I guess. Subtracted A from each side. And then number 6 is I'm going to square root each side. So B squared is equal to square root of 3A squared. So, I square root each side. Now I'm going to simplify, and so that means B is equal to A root 3. So see how, and that's what I was trying to prove. And we could go, that's why it works, I guess, is what I'm trying to say. It's more, I want to show you the rationale more than I want to show you proof. But let me show you the implications it has for equilateral triangles. Let's say that you have this equilateral triangle, and let's call sides A. And as you know, well, let's not even name the sides, okay? Because that's probably not a good idea. All right, but anyway, you have this equilateral triangle, and remember that if it's equilateral, it's equal angular. So it's really a 60, 60, 60. And let's say that I asked you for the area, and all I gave you was a side. And let's say this side is 7. And all 3 sides are 7. Now, in order to find the area, you need this height, right? Now look what happened. When I created that height, I created the perpendicular bisector. Now, the reason why I know that is because if this angle is equal to this angle, these are both rising at the same time. So this apex or this top is actually the midpoint. But let's say I didn't know that. If I just drew this right here, I know this is 90, and I know that this is 60, right? If this is 90, when I drew this segment, this is 60, and every triangle can only have 180 degrees. So that means there's only 30 left here. So what I have is, look at that, a 30, 60, 90, true? Now on this 30, 60, 90, the side that I'm given is a hypotenuse, or the C. So I have a 30, 60, 90, I actually have 2 of them. And I know that the long side is 7, so the C is equal to 7. Using the ratios up here, then A has to be half of that, right? So A has to be 3.5. And this is A, which makes sense. It's going to be half of that. And now my height, my B side, because it is across from the 60 degrees, so it has to be the middle length leg, is going to be B equals 3 root 5 root 3. But let's say I just want to find the area of something. So this time I'm just going to use S. S, S, S. Do you agree that if I wanted to find the area, which is 1/2 base times height, watch now. This is important. If the area of any triangle is 1/2 base times height, I know that on an equilateral triangle, that if with side S, I know the base is S, right? The base is S, and the height is going to be S divided by 2, think about that, times root 3. So the whole bottom, oh, I forgot the 1/2, sorry, 1/2. 1/2 the base, and this is going to be S divided by 2 times root 3 because of this. And let's crunch this. Let's put this together. So that's S over 2, I'm multiplying that, times S root 3 over 2. So what I'm getting is S squared root 3 over 4. And that is true for every single equilateral triangle in the entire world. S squared root 3 over 4 is the area of an equilateral triangle, with S being the side length. So you do want to know this, and you do want to know these things too. Okay, not only for our geometry course, but these are rich for SAT problems. I'm at 12 minutes, and this was an extra video. Wow, you are a dedicated student, or desperate. No, I'm sure you're dedicated. You take care.